So today, complex numbers questions. Again, this material comes from Christos Nicolades' teacher. So thanks to him. So from number 15, two complex numbers, z1 plus z2 equals 3, and calculate the value of a and b. So each of them has a different denominator, so we need to rationalize it to calculate them together. So if you want to make just common denominator, I think it's not very good idea for here, because always complex number with complex denominator is not very easy to deal with. So it's better to make it rationalize. So z1, the conjugate of 1 plus I is 1 minus I. So 1 plus I, 1 minus I, 1 minus I. So 1 minus I squared, which is negative 1, and A minus AI. So this is A minus AI over 2. Z2, B, 1 minus 2I, 1 plus 2I, 1 plus 2I. Again, 1 minus 4I squared, which is negative 4, and B plus 2BI. So now this is B plus 2BI over 5. Now it's time to make common denominator. So Z1 plus Z2 equals 10. So here 5, 5, here 2 and 2. So 5A minus 5AI plus 2B plus 4BI. So here the real part is 10, 5A plus 2B, plus imaginary part is negative 5A plus 4B over 10I. It says this is only 3, which is, it has real part is 3 and imaginary part is 0. So 5A plus 2B should be 30. Negative 5A plus 4B should be 0. So B equals 5 and A equals 4. So number 16. Again, this is the equation of complex numbers. So let me make the rationalization first. So 3 minus 4I, so 9 plus 16, which is 25. And here we don't need to multiply the conjugate. When we have only like a pure complex number here, pure imaginary number, then we can make it only I, because the purpose of this rationalization is make the denominator as a just normal real integer. So this is the simplest one. If we multiply I on both sides, just it is integer. So we don't need to multiply negative 5I because it is conjugate. So negative 5, So negative 5 and zi minus I equals 25 again, 5, 3 plus 4I. So let me multiply 5 here to make all 25. So 3z minus 4zi plus 5zi minus 5I equals 15 plus 20I all over 25. Oh, sorry, it has negative sign here. So here becomes negative like this, because it is like negative 5. So this one, because I need to isolate z to solve it out. So z 3 minus 9I equal 15 plus 15I. So z equals 3, 1 minus 3i, 15, 1 plus I. I prefer to factorize with these common factors because it makes calculation easier. So now I can multiply the conjugate of denominator on both sides. So this is 5. And the denominator is 1 plus 9, which is 10. And 1 plus 3i plus I plus 4i plus 3i squared, which is negative 3. So 2, negative 2 plus 4i, so negative 1 plus 2i. So this is the result of, this is the value of z. And number 17, solve the equation. This is just exactly the same. So A is, we need to isolate it first. So negative 1 plus 5iz equals negative 9 plus 19i. So z, negative 9 plus 19i, negative 1 plus 5i. Negative 1 minus 5i, negative 1 minus 5i. 1 squares minus 25i squares, which is 26. And 9 plus 45i, negative 19i, negative 95 plus 95. So 26, 104 plus 26i. 26 times 4. So this is 4 plus I. What about number B? Because this has a different, this is conjugate. Conjugate sign, this is conjugate and this also conjugate. So whatever it is conjugate. If you have this conjugate sign, it's better to set z as a general expression. So let me put z a plus bi. So 2 plus 5i, a plus bi plus 8 equals 3, a minus bi plus 20i. So on the left side, the real part, I will set only real part first. So 2a minus 5b plus 8 equals 3a. So this is the real part. So a plus 5b equals 8. And the imaginary part, from here, 5a plus 2b. On the right side, negative 3b plus 20. When you compare the complex numbers, only compare between real numbers and imaginary numbers. You don't compare imaginary and real numbers, something like that. So here, 5a plus 5b equals 20. So when we calculate this together, a plus 5b equals 8, and 5a plus 5b equals 20. So negative 4a equals negative 12, a equals 3. When a equals 3, b equals 1. Therefore, z equals 3 plus I. So given z conjugate the magnitude, which is a squared plus b squared, is 2 square root 5. And the complex number z satisfy the equation. Okay. So this is a plus bi, 25, minus a minus bi, 15. So, if we make it common denominator here, because this is conjugate, so we can do it directly like this. So 25, a minus bi, 15, a plus bi, 1 minus 8i. This is the product of sum and difference, which is the difference of squares. So a squares minus bi squares, which is negative b squares. So now here, a squares plus b squares is 20. So now we can use 20. And let me factorize with 5. A minus bi minus 3a plus bi equals 1 minus 8i 4. So again, the only real 5a minus 3a. Oh, we can simplify much easier. So 2a minus 8bi equals 4 minus 32i. So a is 2, b is 4. Therefore, z equals a plus 4i. And this one, complex numbers, simultaneous equations. So it's the same, elimination or substitution. So let me do it. 2z1 plus 3z2. 2z1 plus 2iz2, 8 plus 8i. 3 minus 2iz2 equals negative 1, negative 8i. So z2 is negative 1 minus 8i over 3 minus 2i. So 3 plus 2i, 3 plus 2i. z2 equals 9 and 4, which is 13. So negative 3, negative 24i, negative 2i, negative 16i squared, which is positive number. So 13 minus 26i over 13. So 1 minus 2i. If this is z2, then 2z1 plus 3 minus 6i equals 7. So 2z1 is 4 plus 6i. So z1 is 2 plus 3i. And z2 was 1 minus 2i. And number 20. W is like this. And imaginary part is 0. Then z magnitude could be 1, like it should be 1. So let's try to do that. W x plus yi, x z squared is x squared 2xyi minus y squared. So x squared minus y squared plus 1. I just try to rearrange with this real part and imaginary part separate. xyi. So x squared minus y squared plus 1 minus 2xyi, x squared minus y squared plus 1 minus 2xyi. But this looks so complex. But we want to know only imaginary part is 0. So just let me find only imaginary part, not all. So the denominator is x squared minus y squared plus 1 squared minus but plus because of I squared 4x squared y squared. And imaginary part, this and this when they meet together is imaginary part. So x squared y minus y cubed plus y and negative 2x squared y. You know, when you make imaginary part, it doesn't include I. So only the, not coefficient, but like a coefficient, only the number with I. So this is the one. So this is 0. So if I put y, this and this can be simplified. Negative x squared y. So negative y squared plus 1 negative x squared equals 0. When the fractional expression is 0, it means numerator is 0, not denominator. So this is 0. But it says y is not 0, therefore negative y squared plus 1 minus x squared should be 0. So x squared plus y squared equals 0. X squared plus y squared equals 0. This is magnitude of z. So we proved. And number 21. This is the complex number, and the magnitude of those expressions are like these relations. So here, x plus 16 plus yi magnitude is x plus 16 squared plus y squared. And x plus 1 plus yi, the magnitude equals x plus 1 squared plus y squared. So I just found this and this. So let me put them together. X plus 16 squared plus y squared equals 4. X plus 1 squared plus y squared. When we square them together on both sides, x plus 16 squared plus y squared equals 16. X plus 1 squared plus y squared. X squared 32x, 256 plus y squared equals 16. X squared plus 2x plus 1 plus 16y squared. So when I move them over there, 15x squared. Oh, thank God. 15y squared. 240. So this is 1, 6 x squared plus y squared. Therefore, 4 square root x squared plus y squared. So which is z magnitude. So the answer is 4. And number 22. Confirm 1 is the root of z, fz. So f1 by the factor theorem. 1 cube, 3 1 squared, 7 1 minus 5 should be 0. And 1 plus 2i equals 0. Then 2 complex root of z, f of z is 1 plus 2i and 1 minus 2i. This is conjugate root theorem. So now we have these 3 linear factors. It has this the leading coefficient is 1. So x minus, it's z. F of z, z minus 1, z minus 1 plus 2i, z minus 1 minus 2i. So express as f of z in the form. So z minus 1 stays there. Only this one should be go like this. If you expand them all together, you will solve it out. But if not, I will solve it like this. Z minus 1 plus 2i. Oh, sorry, it's minus 2i. And z minus 1 plus 2i. So if we group them together like this, then this is the sum and product of sum and difference. So now we will make it z minus 1 squared minus 2i squared, which is negative 4. So z squared minus 2z plus 1 plus 4. So z squared minus 2z plus 5. Or actually there is another approach. Anyway, z is 1 plus 2i. Z minus 1 equals 2i. If I square them together on both sides, z squared minus 2z plus 1 equals negative 4. Z squared minus 2z plus 5 equals 0. Same. So this is the square factor. So this was the method 1. And this is 2. Number 23. 4 roots. So I like to write it like this because this looks more clear. Z minus 1, Z minus 2, and 2 here. So the four roots of polynomial is 1 minus 2i, 1 plus 2i, 1 and 2. So expressed in the form of, so again, so if we group them together like this way, this and this, then we can calculate it with this sum and the product of sum and difference. So z minus 1 squared minus 2i squared, which is z squared minus 2z plus 1 plus 4. So z squared minus 2z plus 5. So f of z in the form, so it asks us to expand them all together. Here, when we expand them, z squared minus 3z plus 2. So now f of z should be 2 x squared, z squared minus 2z plus 5, z squared negative 3z plus 2. You can do one by one everything, but my case, this is just my type, my method. I try to find what I want. For example, the descending order. The first one is z to the power of 4, but this happens only once. The next one is z cube, and it happens like here and here only. So negative 2 and negative 3. And next one is z2, is like this, and like this. So 2 plus 6 plus 5 plus z happens like this and like this only. So negative 4, negative 15 plus 10. So this is how we found. So negative 10 z3, 7 and 6, which is 13, 26 z squared, negative 19, which is 38 z plus 20. And number D, sum and product of roots. So sum is 1 minus 2i plus 1 plus 2i plus 1 plus 2. And this makes 5. And negative b over a, negative 10 over 2, which is 5. So these are same. Checked. And p, product, 1 minus 2i, 1 plus 2i, 1, 2. And here 1 minus 2i squared, which is 5, times 1 times 2, which is 10. And again, let's make it like this. Left-hand side, right-hand side. Again, left-hand side, right-hand side. So right-hand side, we want to see e over a. E was 20 over 2, which is 10. So they are together. They are equal. So number 24. Given 1 and 2 are roots. So f of 1 should be 0, f of 2 should be 0 by the factor theorem. 2a, 26, 1 plus 20, b plus 20 should be 0. A plus b equals 28, 48, negative. F of 2, 16, 32 plus 8a, 4, 104 plus 2b plus 20 equals 0. So 52, yeah. So now 8a plus 2b should be 52, negative 156. So now I'll divide by 2 the second one to make the number smaller. So 4a plus b, equals to negative 78. So here, when I subtract them together, 3a equals negative 30, a equals negative 10, and b equals negative 38. So this is the value of a and b. So other two roots, 2, negative 10, 26, negative 38, 20. 1, negative 8, 18, negative 20, 0. And 2, negative 4, 20, 0. So this is the quadratic factor, which is 2x squared negative 4x plus 10, 2x squared negative 2x plus 5. So other roots comes from here. So the quadratic formula, 2, 4 minus 20. So negative 16, okay, 2 plus minus 4i, which is 1 plus minus 2i. So the other two roots, one plus minus 2i. Number 25. This is the roots 1 minus 2i, which means 1 plus 2i, also another root. So now it has quadratic factor, which is z minus 1 equals negative 2i. Z squared negative 2z plus 1 equals negative 4. Z squared minus 2z plus 5 equals 0. So now with long division, 4, 10z cubed, 26z, 38z, 20. Z squared 2z plus 5. 2z squared, 2z to the power of 4 minus 4z cubed plus 10z squared. So negative 6z cubed plus 16z squared minus 38z. Negative 6. Negative 6z cubed plus 12z squared minus 30z. 4z squared minus 8z plus 20. So this is the last one, plus 4. 4z squared minus 8z plus 20. Okay, so this is another the factor, the quadratic factor. So at this moment we express this z squared minus 2z plus 5 and z squared negative 3z plus 2. But this one is easy to do the factorize. So z minus 1 and z minus 2. Therefore, f of z has roots of 1 minus 2i, 1 plus 2i, 1 and 2. That's it. Until here.